All right, it's week 8. Can you get, all right, the end of week 8. It's Friday of week 8. So we just have, and then next week is Thanksgiving. So we're gonna just have 2 classes, Monday and Wednesday. And I mean, I'm gonna cover stuff on Wednesday. If you decide not to come on Wednesday, just watch the video and that's fine. Yeah, question?
Oh, sorry, we can't really hear you.
I know. I forgot my microphone.
Oh, okay.
Yeah, I'm sorry.
No, you're good.
And I got to keep this thing on my face, right? So, yeah. Okay, well, I'll just, yes. Yes. Just hang on. All right. So, all right. All sorts of stuff's happening. Let's, okay, let me post this lecture up. And I still have, I forgot, I didn't post up Monday's slides. So let me do that. Well, I got to like put them into a Word document because it was like handwritten. So I apologize. Okay, well, this is where we left off on Monday, and I didn't get to finish everything I wanted to say. So let me just go back. So kind of what I was trying to build up to on Monday was we brought up the multivariate metropolis Hastings. So yeah, I mean, it feels weird, but you can get up and move closer if it's hard to hear. But come on up, right? At the front row is where it's at, okay? It's not like the movie theater where, okay, so, yay. So what we're trying to say on Monday was that as we do the metropolis Hastings in high dimensions, our acceptance probability gets lower and lower and lower because it's really hard to propose a value that will get accepted. Just in high dimensions, if you just think, you know, in just for example, to take it to the extreme, if only like there's one region where maybe only 10% of your kind of proposal region are good values, in one dimension you'd accept about 10%. But if you have it 2 dimensions and you're proposing these kind of independently of each other, then you only accept 1%. And then with 3 dimensions or 4 dimensions or higher, you just keep proposing the values that you propose. Only a small fraction will be any good and worthy of acceptance. As far as values go. Now, the kind of a strategy around this is the Gibbs Sampler. Okay, and in the Gibbs Sampler, what we're going to do is we're going to take the multivariate thing and factor it into a bunch of univariate ones, a univariate conditional distributions that multiply together. And then we can just propose one coordinate at a time. And so generically, it looks like this, which admittedly is a bit of a mess, okay? So if we have something in d dimensions, we first say we're going to generate x1. We propose x1, okay? Well, actually, not even propose x1. Now that we've factored it into univariate, now you just generate from x1, okay? You just generate from x1. And then once you've generated a new x1 for the next time iteration, x at time t plus 1, you include that into the next value. Now we want to generate x2. x2 is going to be conditional on the x1 that we just generated, plus all of the other values, x3, x4, x5, up through xd. And then we generate x3 based on this conditional distribution. We're going to generate x3 based on the new values of x1 and x2, and then the older values of x4, 5, 6, up through xd. Okay? So let me just show you what the Gibbs sampler would look like for just a simple two-dimensional multivariate distribution, okay? So let's say we have a multivariate normal distribution. This is what we want to do. And this is kind of what it would look like. Do you guys remember, well, if you took 102A with me, we covered coordinate descent, okay? And coordinate descent was an optimization method, and we were trying to find the bottom. We isolated it. We made the distribution conditioned on one particular value of x1, and we found the optimal x2. And then once we found that, we conditioned it on x2, and we found the optimal x1. This is a little bit, there's a similar idea happening here, except we're not trying to optimize it. We're trying to generate a sample from it. Okay? So what we do is we condition it on, let's say we want to get the next value for x1. We condition it on x2. When you do that, so the overall distribution is multivariate in x1 and x2. You have a multivariate Gaussian, but you condition it on x2, this particular value. And if you do that, now it's a univariate normal distribution. It's just a regular normal distribution with some mean, some standard deviation. The mean is right around here. The standard deviation is some value. And what we do is we just say, give me a random normal value, okay? So we say, here's the distribution. Give me one random normal value. Now, because it's random, it could be right in the middle. It could be over here. It could be over here. It could be wherever you want, right? Not wherever you want, but just it's going to be random, okay? And so I'm just saying, let's pretend we got this value right here, this blue value, okay? We're going to say, okay, this is my x1 value. So here, this is kind of my starting spot. We condition it on x2, and then we say, all right, draw a new value for x1. I draw a value for x1, and now I condition it on x1. When I condition it on x1, the multivariate distribution, again, we're going to have a univariate distribution. It's just a normal distribution of one variable centered now over here. And we're going to just draw a random value for x2. So we're just drawing random values for x1 based on our current value of x2. And then we draw a random value of x2 based on our current value of x1. And we kind of go back and forth because there's only two dimensions here. But if we had higher dimensions, you could just do each variable one at a time, continuing to generate just a new value from the univariate. So you would use our norm, and you'd have to specify the mean. You'd have to specify the standard deviation. And so I just posted homework 5, okay? And in homework 5, you have to do the Gibbs sampler. And I left out from the slides and the notes, what would the conditional distribution be for like a multivariate Gaussian? For a multivariate Gaussian, you'll have to figure out what that conditional distribution is. It's a little bit tricky. So I've linked to kind of a chapter from a textbook where it talks about the multivariate distribution, and what you want to find is basically turning it into a conditional distribution. And so you'll read through that. The answer is there, but you have to be able to read and know where that answer is, okay? So that's there, okay? And so your next coordinate, so once you get x1 at time t plus 1, and then you get x2 at time t plus 1, then this will be your new x coordinate. X at time t plus 1 will be kind of these two things. And then it goes back and forth. You're going to get x at time t plus 2 based on your current value of x2. And then once you have that, you'll get x2 at time t plus 2 based on your new value of x1. And it continues going so on and so forth. And that will be that's what you will see, okay? Now, in your homework, I'm going to have you do both the kind of Metropolis-Hastings algorithm for multidimensional, where you just kind of generate values x1 and x2 independently, and then you'll also do the Gibbs Sampler. And what you will find is that both of them, you can start at this terrible location, and both of them will eventually find the good area, okay? The Metropolis-Hastings will take longer, just because it's proposing x1 and x2 completely independently, at random, things like that. The Gibbs Sampler, it's proposing based on a conditional distribution, and so it's going to find something a lot better, a lot more quickly. All right. Does that kind of make sense? Okay, let me go ahead and give you your first view quiz answer. Today's first view quiz answer is A. I think A as an apple. A as an apple. Okay, and then and I want to introduce hierarchical Bayesian models is, I guess, the full thing. Okay, and here's the Gibbs Sampler, and the Gibbs Sampler, requires us to factor our joint distribution into a bunch of univariate distributions. And factoring that work, that can be hard sometimes. It can be hard, right? But a hierarchical model is set up in a way that the factoring is like, it's easy, okay? So, so just again, symbolically, we get x1 based on all the old values at x at time t. You get the next value x2 based on your new value of x1 at time t plus 1. All the old values this should say x3, so on and so forth. And anyway, we keep going. All right, so the hierarchical models are set up using conditional distributions. So deriving the conditional distributions themselves aren't even necessary. It's just part of the hierarchical model, right? So what we're going to do is we are going to go all the way back to the Bayesian baseball model, the beta binomial model, where we've got where we're looking at the baseball player and we're trying to figure out the player's batting average, right? So do you guys remember this setup? We said, before we look at the data, we know that players' batting averages generally are going to be between 0.2 and 0.3, and our prior distribution has a mean of something around 0.27-ish, something around there, maybe a little higher, maybe a little bit lower, okay? And we say every player has some mystery theta distribution, or some mystery value of theta, and we are treating this value theta as a random variable. So it has its own probability distribution. And so we say, there's a prior distribution for theta, and we chose a beta distribution with shape parameters 81 and 219. And I admitted, and I said, hey, the choice of 81 and 219, this is a little bit arbitrary, right? This might have felt a little bit uncomfortable. But we picked them because the resulting distribution produced, looked like the way we wanted, right? Most of the values above 0.2, almost all the values under 0.35, something centered around 0.27, okay? So in a hierarchical model, we say, I'm a little bit uncomfortable with the idea of just setting in stone the prior distribution parameters, 81 and 219. And we say, what if we treated that number, alpha, 81, currently 81, what if we said alpha is a random variable? What if we said that number 219 beta is also a random variable. So it's not really set at 81 and 219, but what if we treated them as random variables? And they are unknown to us, and we do something like that, okay? So now we've built up this hierarchy, all right? We say this value theta comes from a mystery beta distribution with shape parameters alpha and beta. And before we said alpha was 81 and beta was 219, but now we say, well, what if alpha and beta were random variables and they came from some other distribution, right? So now we have this. So we have the prior distribution, which is our beta distribution. And now we have what we call a hyperprior distribution, okay? Because this is a higher distribution that is generating the values of alpha and beta, okay? And so the shape parameter alpha is a random variable that has its own distribution. Beta, the shape parameter beta, is also a random variable with its own distribution. And alpha and beta, we call these things hyperparameters, and the hyperparameters come from their own distributions called hyperprior distributions. So these are hyperprior distributions. So the random distributions that produce alpha and beta are known as hyperprior distributions, because they produce the hyperparameters alpha and beta, which define our prior distribution. It's like word soup here. Okay? Now, the hyper distributions themselves, the hyperprior distributions, if they also have their own parameters, those would be called hyperparameters, okay? What's that? Did you say boo? Yeah. Okay, all right. 100% serious, I'm not joking, that they're hyperparameters, okay? And we could kind of, and you can keep going, right? It's like prior parameter, do you guys even use the word inception to kind of, this idea of like, it's just nested inside of each other, right? I don't know, like, I feel like that cultural reference will go away fairly soon, because that movie's now already 11 years old, so I don't know. Okay, so it's like prior distribution, hyperprior distribution, inception, and you can just keep going and going and going. At some level, you got to stop the craziness, right? And so at some place, you kind of select something, but basically, the more levels you're removed, the less like particular influence it has, okay? So we generally we'll stop after a couple layers here, okay? So we ask, well, what should we do here, okay? The values alpha and beta, which in our old Bayesian model, we said, I'm gonna pick 81, I'm gonna pick 219. Now we want to say 81 and 219, these should be the result of some random process, okay? And so if we think, well, what does 81 and 219 represent even? We might call these things pseudo counts. Because remember, if you remember the beta binomial distribution, like when we observe our player have at-bats and have hits, we update our distribution by kind of adding the count of hits and the count of misses to kind of the shape parameters, and we updated our distribution. And so this idea of 81, 219 is as if we had already pretended we've observed the player get 81 hits and 219 misses. And this is kind of now my fake imaginary data, which we call, the pseudo counts, right? So we say prior to seeing data from the player, we're just going to pretend that the typical baseball player who ends up qualifying for the major leagues may have 81 quote unquote like imaginary hits and 219 imaginary outs. does that kind of feel okay conceptually? This idea of like, I'm going to just pretend that this has happened, okay? And again, they're not actual values, they're just imaginary things, okay? And when we do this, it will have a beta distribution where the peak is 0.2685. Not, the mean is 0.27, but the mode, if you remember the formula for the mode is alpha minus 1 divided by alpha plus beta minus 2. We get just something under 0.27, okay? 0.2685. That seems kind of reasonable for a batting average. And we can arrive at these numbers, 81 and 219, by taking the total number k, 300, taking omega, 0.2685, and we say alpha is going to be k minus 2 times omega plus 1, right? And if you do this, you'll get 81. And then you'll get beta by doing 1 minus omega times k minus 2 plus 1. And we get 219. Okay, it's just a little bit of algebraic work to kind of get back 81 and 219, these two values from these two values. So we can kind of express, so rather than picking alpha and beta as kind of the number of hits and counts, we can kind of say, re-express it as the total number of observations, 300, and maybe our current peak is located at 0.2685, okay? And this gives us basically something, all right? And so with this, I'm going to, we can treat k as an arbitrary selected constant of 300. Just so my model doesn't get too complicated, we could treat k as a random variable, but let's just say we're going to keep k at 300, and we're going to just alter omega, okay? So that way my hyper-prior distribution only has 1. I'm only going to try to model 1, rather than modeling alpha and beta. Is that okay? All right, and so if I pick omega, this w, it's not w, it's omega, I don't know, whatever, okay. Omega, if I pick this to be, 0.27, I'll get a slightly different alpha and beta. If I pick it 0.25, I'll get a slightly different alpha and beta, so on and so forth, okay? And so, so here, we're going to say omega itself comes from a beta distribution. And here, the beta distribution that determines omega is what we call the hyper-prior distribution of omega. We use that to figure out what our alpha and beta are. We use alpha and beta to then get our theta. I'm sorry. Okay. I'm trying to describe the hierarchical model. It just feels like there's so many words here, and I apologize, okay? So now that we have a hyper-prior distribution, and that's a beta distribution, we also need shape parameters for this hyper-prior distribution. So we need these hyper parameters, alpha underscore omega, or A underscore omega and B underscore omega. Let me just show you the picture. Maybe this helps. So we have this hyper-prior distribution. This is a beta distribution. This beta distribution is shaped by shape parameters A underscore omega, B underscore omega. All right. And from this beta distribution, we are going to draw a value for omega. Omega may be 0.26, might be 0.25, might be 0.27. Omega will determine where the peak is for our prior distribution, okay? And we get our shape parameters for our prior distribution by using k and omega to get back basically our alpha, and k and omega to get back our beta, right? Because there's this relationship of omega times k minus 2 plus 1, 1 minus omega times k minus 2 plus 1. And that gives us our beta distribution, which is our prior distribution, and from that, we draw the player's batting average theta, and that theta, the player's batting average, determines via a Bernoulli random process, it determines the observations we get, the hits and the misses in the actual data. Right. Is this diagram okay? Yes. Oh, okay. Thank you for that thumbs up. Okay, so these are all of the terms in our hierarchical model. Here we just have k set to 300, arbitrary constant. And again, you could model k as a random variable now, but then you'd have two hyper prior distribution, and I didn't want to do that just right away. Okay, they do that in the textbook if you read chapter 9 in the puppies textbook. Okay, so we're going to draw omega from this hyper prior distribution. The shape parameters alpha and beta are determined by omega and k using these formulas. These shape parameters alpha and beta go into this beta distribution where we draw the player's batting average theta. And now that we have this player's batting average theta, we generate our Bernoulli, using a Bernoulli distribution, we generate the actual values of the hits and the outs. Okay. Let me give you your second view quiz answer, which is E. E as an elephant. E as an elephant. Okay. Why did we torture ourselves building this hierarchical model? What advantage would this provide? Okay. Well, now we have a model that could be used to describe different players and their hits. Okay? So we could say there is some ultimate batting average random distribution something up here. Okay? Right? And we're drawing them from this kind of this beta distribution, right? But we don't want to just pick 81 and 219 and say that as a thing, okay? So we're going to have a hierarchical model. We're going to say every player has their own batting average, theta sub s. Now we're going to not look at just one player, but we're going to look at like a team of players or the league of players or something, okay? A division. Every player has their own batting average theta sub s. Player 1 has batting average theta 1. Player 2 has batting average theta 2. Player S has batting average theta s. Okay, so what does this look like? Basically, we say, all right, every player's batting average theta s comes from a beta distribution. Okay. It's randomly drawn from a beta distribution. Again, this beta distribution has shape parameters alpha and beta. Alpha come from this. And again, we are not setting these in stone at 81 and 219. We're allowing them, we're treating these as random variables. Alpha and beta are the result of randomly drawing in omega and multiplying it by k, basically. Okay. And again, the outcomes of one particular player, right? So we look at one particular players and the outcomes they get, the hits and the outs. We look at another player, we look at their hits and outs sequence, okay? Every person's thing is conditioned based on which player is generating those hits and outs. All right, so this diagram looks almost identical to this diagram, okay? Except the only thing that's different is if you look at these two things here, rather than just drawing one theta, we're drawing different thetas for each player. We have a theta sub s. A theta sub s because we've got s different players or a bunch of different players. And so it's almost the same thing, but now we're accounting for multiple players, each one having their own batting average. All right, and then so the values that we generate depend on which player we're talking about, right? So this is kind of the diagram that we have, okay? And forgive my artwork here. So here's we have a hyperprior distribution. From the hyperprior distribution, we generate an omega. The omega combined with the k determine the alpha and the beta. Here, the alpha and the beta, these are deterministically related to omega. We just do omega times k minus something plus 1, and omega 1 minus omega times k minus something plus 1. They are deterministically related. We take these two shape parameters, alpha and beta, and they feed into our beta prior distribution. And our beta prior distribution can be used to generate theta 1, players theta average theta 2, player theta 3, player theta 4, so on and so forth for more players. Player 1 has batting average theta 1, and we use a Bernoulli distribution or Bernoulli random variable, and that generates a sequence of zeros and ones. Out, hit, out, hit, okay? Player 2 has a different batting average, a different theta 2, that goes into the Bernoulli and generates a sequence 1, 1, 0, 0, whatever it is. Player 3 has a different batting average, different values, okay? Now all of these, because they're coming from the same beta distribution, these thetas will probably not be wildly different from each other, but they will be different, and therefore the values that we see also, and again, they're random things, right? It's like you kind of need a lot of values to, really detect some of these differences, right? If you've got a coin that lands heads 27% of the time, and someone else has a coin that lands heads 23% of the time, you really have to be doing a lot of flips to really kind of detect those kinds of differences. But anyway, this is kind of the model that we're using. Is that okay? And so this diagram here, there's also something called a plate representation. And if you start getting into technical papers, you might see diagrams represented with plate diagrams, okay? Plate diagrams instead. And this is basically the same information here. It's just rather than drawing thetas and Bernoullis and things like that multiple times, they just put a box around it and they put a little subscript in the corner to say this thing is going on a whole bunch of times. So we're saying, you'll see something like this. Shape parameters alpha and beta determine our beta distribution. From there, we generate a theta value, theta sub s, and from the Bernoulli, we generate our y sub i's. We put a box, a plate, with a subscript s to indicate that this is going on for all of the s different players. And so this is like a simplified representation of this process over here. And that's our hierarchical Bayesian model. Okay, so how does this work? Okay, well, we're going to do this, and we can kind of set up, our Gibbs Sampler and things like that to kind of do this. But so let's say we've gathered all of our data. We've got a big matrix of data of all the hits and outs of, say, 40 different players. All right, so you got 40 players on a team or something. I don't know, I guess half of them are pitchers, but But let's say we got, a whole bunch of players, and we're going to say observation or random variable y sub si is going to be either the hit or the out of player s, all right? And you've got I of these, right? So they might have a whole bunch of hits and outs. And we want to get estimates for all of these unknown parameters. Every player has its own theta sub s, right? And so we have a whole bunch of parameters to estimate, okay? And so we have 40 different theta sub s values, okay? Because every player has their own theta value. So when we did the beta binomial way earlier, we only had just one theta value to estimate based on, we just had one posterior distribution for that one player's theta, okay? Now that we're doing kind of this hierarchical thing and we're looking at a team, we've got 40 of these theta values to estimate, okay? And we also have to estimate omega, which we use to determine alpha and beta, okay? We're going to say these other parameters that are part of our model, the k, which we've arbitrarily selected to be 300, and the hyper parameter of a sub omega and b sub omega, these have been arbitrarily selected. We're not going to try to infer these from the data, but we're going to use the data to figure out our theta sub s values as well as the unknown value omega. Okay, so I've got 41 of these values to figure out, right? And we're going to say, so all of these theta values are not, if you think about that, they're all kind of, in this thing, when you look at the theta values, we expect them to have correlation or to be kind of related to each other because they're coming from the same beta distribution, okay? However, once you condition them on the beta distribution, the values that you generate will be independent of each other, right? So once you know that beta distribution that's generating the different thetas, then the different thetas that you have can be treated as independent of each other, right? So prior to conditioning it, we would expect all of these things to be related, right? So, man, what a slide this is. Okay, so if you think about the total posterior distribution, we've got 41 random variables, and we want to figure out the posterior distribution of our 41 random variables given all of the data that we've collected in matrix Y, all of the hits and the outs that we've seen, plus these three parameters, the hyper parameters that we have just arbitrarily selected. Okay, and again, you can always kind of model these hyper parameters as random variables, but that just will complicate your model even further. So we're going to avoid doing that for now. Okay, so we can so we're going to say this again. In all of these things, the A, B, and the K are selected, so we're not going to bother trying to model those randomly. We're going to say, okay, the posterior is the likelihood. What is the likelihood of getting our matrix data Y given all of these parameters, theta 1 through theta 40 for 40 different players, plus that omega? Okay, and then we have to say, well, what's the prior distribution for all of this given these parameters, and then, divided by the marginal Y? Well, we say, well, this thing we're going to ignore. It's just a constant. And we have this, okay? And truly, if you take this, what's the product of Y given this and this given this, right? It's just the joint distribution, right? It's just the joint distribution, right? A given B times B is basically A and B, right? The probability distribution of Y and all of these parameters given these things, okay? So the last row here is just the joint distribution of everything. And again, because of the hierarchical nature, the hits and outs of player 1, Y11, Y12, all the way through Y1I, only depend on the batting average of player 1. Okay? The hits and the outs that we get, this sequence for player 1, only depend on this theta 1. We don't need to factor in all of this other stuff for the other players. Okay? So this hierarchical model allows me to factor the whole distribution into a whole bunch of conditional distributions, which is kind of the perfect setup for a Gibbs sampler. So we're going to say this whole joint distribution, we can factor it into a whole bunch of different probability distributions. It's a huge product, but it works out. We're going to say row 1 in our matrix Y depends only on player 1's batting average, theta 1. Row 2 in matrix Y only depends on player 2's batting average, all the way, and same up to row 40 for player 40. Okay? And then what about player 1's batting average? Okay? Player 1's batting average basically depend only on the beta distribution, omega, which is determined by omega and k. And player 2's batting average, theta 2, depend only on its prior distribution, which depends on omega and k, all the way up through here, where omega, we have to figure out, okay, well, what's the probability of getting omega given, again, the values that we've arbitrarily selected, k, a sub omega, and b sub omega. And maybe I'll just pause here and just make sure that factoring this joint distribution into a product of a whole bunch of things. This is like 81 terms here. I just kind of want to make sure that this makes sense. Yeah?
That last term, how does omega depend on k?
Oh, I guess it doesn't. You're right. It's good. Good catch there. Okay? So omega just is determined by a sub w and b sub w, or b omega, and does not depend on k. Yeah. Okay. So we have factored this out, a whole bunch of stuff, and we'll set up our Gibbs sampler that takes advantage of this structure, which is a whole bunch of conditional probabilities, right? So we factored this, we've got 40 individual batting averages, theta sub s, along with omega here, okay? And so each row is basically the result of the random draws from a Bernoulli distribution. Each player's batting average, theta sub s, is the result of a random draw from the beta distribution. And the value omega is a random draw from the beta distribution, where, we don't need to include the k. And those are just the a sub omega and b sub omega. We have just arbitrarily determined these things, okay? And so I guess next week, we'll create the Gibbs sampler that will say, all right, can we just draw these things from each of these different kind of distributions individually, one at a time, and we'll do that. Okay, so that's what we'll do next week. So we'll end here for today, and we'll see you guys then. All right, so have a good weekend. I've posted up a homework assignment, and so go ahead and you can get started on that, and we'll see you guys on Monday. Yeah, question. Oh, last view quiz. What was it? B, I think. B. I don't know. I'll make sure it's B, okay? B as in bear. B as in bear. Last view quiz answer. Okay. All right. Thanks, guys. We'll see you Monday. Have a good weekend.